Welcome to my talk. I'm going to talk about cohomology of solved manifolds. Start from classical theorem proved by Nomis. Let's G be a simply connected nilpotent regroup with real algebra. Assume G has co-compact discrete subgroup gamma. I shortly call it lattice. Then we have an isomorphism between real algebra cohomology and drum cohomology over nil manifold G over gamma. The real algebra cohomology is the cohomology of a finite dimensional cochain complex, and drum cohomology is the cohomology of infinite dimensional cochain complex. So we can compute the drum cohomology of a nil manifold by a finite dimensional cochain complex. So it's very nice theorem. The main interest of this talk is to extend this theorem to solvable case. This was done by Hattori. For special solvable case, he proved that let G be simply connected completely solvable regroup. Completely solvable means that G is solvable, and for any element of G, the all eigenvalues of adjoint operator are real. In this assumption, like a nil manifold, we also have an isomorphism between the real algebra cohomology and the drum cohomology of a solved manifold G over gamma. By Hattori's theorem, we can compute the drum cohomology of solved manifolds, special solved manifolds, by the real algebra. So it's natural to hope that this is also true for general solved manifolds. But it's not true. Let's check this on the example. Let G be the semidirect product of L and L2, so that the action of L on L2 is given by rotation matrices. Then we have a lattice 2 pi z and z2. The action by rotations is trivial on 2 pi z. So the solvmanifold gamma is actually a tritorus. This implies that the first bit number of gamma is equal to 3. Otherwise, the real algebra G is three-dimensional, non-abelian real algebra. So the dimension of the first cohomology of real algebra G is smaller than 3, since this space is that this dimension is equal to the dimension of G over commutator ideal. Therefore, we don't have an isomorphism between the algebraic homology and Durham cohomology of G over gamma. I'm interested in computing the Durham cohomology of solvmanifolds, even if the isomorphism between the algebraic cohomology and the Durham cohomology does not hold. I introduce my results on this. Let G be a simply connected solvable group without any other proper conditions. Assume that G has a lattice gamma. Then we can construct an explicit a gamma in the Durham complex of G over gamma, which is finite dimensional subdifferential graded algebra. So that the inclusion induces an cohomology isomorphism. By this theorem, we can compute the drum cohomology of solved manifolds even if we don't have isomorphism between the real algebraic cohomology and the drum cohomology. I'll explain precisely this theorem later. Next, I will consider durable cohomology of solved manifolds. It's very important because there are many non-Kähler solved manifolds. So even if we can compute the drum cohomology of solved manifolds, we should compute durable cohomology also. There is a result on the durable cohomology of Needle manifolds, like Nomi's theorem, proved by Sakane. Let G be simply connected complex nilpotent regroup with the real algebra over C. We assume G has a lattice gamma. Then we have an isomorphism like this. This means that the durable cohomology of G over gamma is computed by the real algebra cohomology of G. So we can compute the durable cohomology of complex parallelizable Needle manifolds by using real algebra. Like drum cohomology, we cannot compute the durable cohomology of complex parallelizable solved manifolds by only using real algebra. But I also compute the durable cohomology of complex parallelizable solved manifolds. Let G be simply connected complex solvable regroup. Assume G has a lattice gamma. Then we can construct an explicit B gamma in the Dorbo complex of G over gamma, which is a finite dimensional subdifferential graded algebra, so that an isomorphism hold. So by this theorem, we can also compute the Dorbo homology of some manifolds, complex pairs of some manifolds. I noticed that Sakane's theorem is now generalized to more general complex Near manifolds. Maybe this will be explained in detail in Lawrence's talk. In this series, the G is simply connected real nilpotent regroup with a left invariant complex structure. J, we assume G has a lattice gamma. Then under some assumptions, we have an isomorphism between the Dormo complex of real algebra and Dormo complex of the Near manifold with the left invariant complex structure J. I gave extension this result to a solvable extension. We consider the case G is a semidirect product of complex abelian Lie group and simply connected nilpotent Lie group. With rest invariant and phi invariant complex structure. Assume G has a lattice gamma which is compatible with this semidirect product. Then and some assumptions we can construct finite dimensional subdifferential bigrade algebra of durable complex of G over gamma, so that this inclusion induces an isomorphism based in the cohomology. I explain an idea for constructing DGA or DBA for drum case. For any solid manifold, G over gamma we have a canonical fiber bundle structure over the base torus, a torus over a torus with fiber near manifold. Then we can compute the cohomology of base and fiber by finite dimensional DGAs. So by using these two DGAs, we can construct a DGAs in the Durham complex of G over gamma. So that this induces the inclusion induces an isomorphism between the second term of spectral sequences. The idea for Dolbeau case is very similar, but to use this technique, we need the homomorphic vibration structure of a torus with a base Needle manifold with a left invariant complex structure. For my two cases, complex parallelism solved manifolds and solvable extension of Needle manifold, nilpotent case, we can obtain a nice holomorphic fiber bundle structure on G over gamma like this. Now we can only compute Dolbeau cohomology of special type solved manifold, complex solved manifolds. So I would like to suggest the conjecture for simply connected solvable group with left invariant complex structure with lattice gamma we can construct an explicit finite dimensional subdifferential bigradal algebra of Dolbeau complex of G over gamma, so that the inclusion induces an isomorphic homology isomorphism. But we have a difficulty for this conjecture. Unlike complex solved manifold case or solvable extension of nilpotent case. A good holomorphic vibration may not exist on the solved manifold G over gamma with a left invariant complex structure in general. Let's consider important examples, OT manifolds. These are non-scalar complex manifolds constructed by Otto and Thomas. We can see them as solved manifolds. See my paper in Bulletin of London Mathematical Society. Consider an algebraic number theory, number field of degree s plus 2t. S is a totally real degree and 2t is complex degree. Then associated to K, we can construct a lattice the home of semi-direct product U and some group U and OK is the abelian group of algebraic integers of K. Lattice of the real algebra the group G. G is of the form like this. So we have some manifold G over gamma. This is an OT manifold of type SD. On this G, we have a left invariant complex structure. So that G is bihomomorphic to S times upper half plane and direct product of S times upper half plane and CT. So we obtain a solved manifold with a left invariant complex structure. On this complex solved manifolds, we don't have a nice homomorphic fiber bundle structure. We only have real fibration, non-homomorphic fibration over Ts with base S plus 2t torus. So we cannot apply my construction like complex parallelizable case or solvable extension of nilpotent case. On the other hand, recently, very recently, Otto and Thomas gave very nice result on OT manifold. They prove that we have hot decomposition on the cohomology of OT manifold. I think it's a very nice advance for computing durable cohomology of orthogonal manifolds, because we can compute the durable cohomology of complex solid manifolds which do not admit good holomorphic fibration. I try to understand the key part of Otto and Thomas theorem. I think it's like this. For the subgroup of a lattice gamma, the coefficient G over OK, this is a non-compact solid manifold. This non-compact solid manifold has only constant holomorphic functions. Non-constant holomorphic functions. This implies the finite dimensional durable cohomology of non-compact manifold. This is the theory of Cousin group or toroidal group. Theory of non-compact quotient of complex abelian Lie group. I hope that this type of argument will be applied for more wider complex solid manifolds. So my more precisely conjecture for computing durable cohomology of solid manifolds is written like this. For complex solid manifold, G over gamma without good homomorphic fibrillation. We have there exists Cousin group type structure. I don't know what this is precisely, but maybe take a some subgroup of gamma, and then the quotient of G over this group has a finite dimensional double cohomology, like OT manifold. And apply this, by applying this, we can construct express the dBA of Dolbeck complex of G over gamma. The inclusion induces a cohomology isomorphism. I think this is very interesting problem to consider the Cousin group type structure on solved manifolds with rest invariant complex structure. At last, I will explain the detail of my constructing DGA for drum case. First, we consider splitting case like this. G is a semi-direct product of abelian Lie group and simply connected nilpotent Lie group with semi-simple action. Semi-simple means that phi induces a semi-simple action on the real algebra of N. So we can take a basis of N tensor C so that this phi represented by diagonal matrices. For this, we can write the real algebra complex as left invariant differential forms like this. Here, Ti is Ti is the parameter of Rk, and small x1, xn is the dual basis of x1, large x1, xn. Assume G has a lattice gamma which is compatible with the semi-direct product. Now define vector space A gamma like this. With DTI tensor, the graded vector space generated by xi, I is so that I is a multi-index in between 1 and n, and the restriction of the character alpha I on gamma prime is trivial. Xi is the product through the multi-index I, and alpha I also a product through multi-index I. Then this space is actually sub-DBA of DGA of Durham complex, and this inclusion induces a cohomology isomorphism. Let's see this on example, on the simple example. As I said before, the semi-direct product of R and R2, so that the action is given by rotation matrices. Then take a basis of R2 like this. Now that is the parameter of R2. Then the action is represented by diagonal matrices. And that the diagonal entries are exponential IT and exponential minus IT. Consider the lattice 2 pi z and z2 So for this, we should check the restriction of 2 pi z on EIT and minus it. Now, obviously, they are trivial on 2 by z. So we have a gamma is given like this. So we can compute the drum cohomology of 0 by gamma like this. This is the same as the tritorus. I remark that we also have another lattice pi z and z2. In this case, the restriction of EIT and E minus IT on pi z are non-trivial. So A gamma is given by like this. So for such other lattice, we obtain different cohomology like this. And general case is similar to splitting case. For let G be simply connected solvable regroup with a real algebra. Now we consider the nil radical of G. This is the maximal nilpotent ideal of G. Then for this, we can take almost splitting like semi-direct product. We can take a subvector space, not sub-real algebra of G, so that G is a direct product of vector space V and N, and the map, which is taking the semi-simple part of the Jordan decomposition of add x. X is the component of V. This is real algebra homomorphism. we can take a vector space like this. Since this is a real algebra homomorphism, we can extend this on the group G. Since this is semi-simple, we can take a basis of G tensor C so that this other SS is represented by diagonal matrices. Suppose G has a lattice gamma. We define a gamma like this, as similar to splitting case. Then this is a sub DGA of Durham complex G of a gamma, so that the inclusion induces a cohomology isomorphism. So by this construction, we can compute the Durham complex of solved manifolds by the finite dimensional sub-cochain complex, even if we don't have an isomorphism between the algebraic cohomology and the Durham cohomology. So thank you for your attention.